we are going to talk about insulation. So, Cam, what is insulation?
Well, I think we need to start, what is insulation is about reducing heat transfer.
Yep.
But in order to understand how insulation works, we need to understand how heat transfer works. So there are three ways in which heat can transfer: conduction, convection, and radiation. So we take each of those one at a time. Conduction is a material property. So different materials have different rates at which heat conduct across them. And conduction is about the atoms within a lattice of a solid material like metal or glass, for example, or even timber. And heat is energy. It's the excitation of those atoms. So they vibrate. Yep. And when they vibrate, they hit the atom next to them and they transfer that energy. And they do that across that solid material. That's conduction. So that conduction is something that happens across a solid. Convection is the movement of air. It's air, warm air from one space moving to a cooler space, carrying heat energy with it. And that happens a lot in our buildings and is one of the reasons why air tightness is so important to energy. And the third one is probably the trickiest one conceptually to understand, and that's radiation. That's electromagnetic energy. So a material, when it's heated, will emit radiation in all directions, and then that will transfer to an adjacent material and be absorbed. So this is about the characteristic, and this is where colour becomes important, because different materials have different rates at which they emit electromagnetic radiation and absorb electromagnetic radiation. So a material that's a dark colour, like black, will have a higher absorptance, which is a better ability to absorb radiant energy, and a light colour will tend to have lower absorbed.
So you're saying that with all these councils and local governments now wanting to remove black roofs, that could potentially be in a climate where we cool climate, but we need a heat, that could be a bad thing?
Well, it depends. So colours like dark claddings can be beneficial too. So in a heating-dominated climate like Melbourne or a Canberra or somewhere, it is true that a darker colour roof sheet will obviously make that roof space significantly warmer on a warm day than a light-coloured roof sheet. But it also means that the system is drier because you have much greater drying potential within that roof space because of the ability for that to absorb the heat and then allow drying.
So maybe a bit off topic for a second with this. Is it the heat urban island effect? Are the roofs that we're designing, like, should we be going more lighter colour or darker colour?
I think heat urban, I think that is about landscape and concrete mass, rather than and lack of trees.
Yeah, this is where I'm actually. This is actually what I wanted to get at. It's like, are we blaming the wrong thing for this issue?
Well, I think it can contribute. I mean, if you look at a satellite image of an urban suburban area, obviously the roof area is a significant part of the total fraction of that surface area. But the roads, asphalt, the dark colour, is 30% of our surface area of our seas is road. Yeah, so that's going to contribute disproportionately. So yes, to an extent, I think this is somewhat overplayed. But if we just bring it back to buildings for a second, if you design your building envelope well, the colour of the cladding and the roof sheet are far less material than if you design your building poorly.
I actually have a note down here saying dark colours, does it matter in passive house, or we could extend that to high performance homes. And I think we've kind of touched on this before in other podcasts where we start talking about that ventilated and drainage cavity, because does a light or dark roof actually have that impact given its, I guess, separation from that insulation layer?
If that cavity is really well ventilated, then clearly the colour of the cladding is far less important.
Yep.
But there will always be some heat transfer from the roof sheet through the cladding into your insulation and then into the building itself.
Yeah.
But as you go up through from code to high performance to passive house, the effect of the cladding colour on performance of the building declines. Yeah. So yes, it's still important, but it's secondary or tertiary versus to so many other things that you can do with your building. Whereas if you have a really poor building, co-built building, then yes, the cladding colour absolutely has an effect. And so if you put Monument on the roof, then in the summer in Western Sydney, you're going to bake.
So you say poor performing house, but we had a passive house in Ascot Vale where originally the designer designed it with a darker color to get the PHBP across line, but actually it was a white. And by the end of the project, which I had no idea about this and the clients had no idea, it was actually white, and we lost 1 kilowatt hour across the whole building, which meant we were now failing.
And so this is where context matters, I think, because 1 kilowatt hour per square meter per annum, which is like part of these metrics for using passive house, is really significant when you're targeting something like 15, which is this magic number. So 1 divided by 15 is obviously a large number, but we need to bear in mind your code-built homes are north of 100.
Yeah.
So 1 unit out of 100 is diddly squat. 1 unit out of 15 is really material.
And just to close out the whole dark color versus light color thing, that would probably have an impact, more or less of an impact, if you had a cold roof scenario and a warm roof scenario, I'm questioning. Because, and I'll probably let you expand on that a little bit, because it does then feed into insulation, then where insulation sits and its impact in a building.
Yeah, it can do. So if it's a cold roof, again, it depends how well ventilated that roof space is.
Yep.
But you've got a bigger...
I love these sort of like, well, that depends, because every situation is different. And I think that's actually really important to acknowledge.
And I think this is where we come back to rules of thumb. You know, we talk about like the NCC talks about this, you know, you need so many square millimeters per linear meter of opening in order to ventilate a wall or a roof. And we have all these rules of thumb, and they are based on 1 or 2 empirical studies in Germany, Austria, New Zealand, wherever it may be, with one context, one wall type, maybe a few different ones. That doesn't necessarily apply to your particular brick veneer project in kind, or wherever it may be. And so context matters. Understanding the physics of what's going on matters, because you can use that rule of thumb to then say, well, that's my starting point. But my particular project has these particular attributes, which makes it riskier. Therefore, I err towards having more ventilation. Yeah. But on the other hand, this project has these attributes, which makes it less risky, so I can be a bit more, not have to require as much in the way of those openings.
So history of insulation, we probably think back to like the house I live in now, something built around like 50s, 60s, nothing. We've gone from nothing to having something, but now introduced a problem.
Yeah, and so what are we doing insulation for? We're trying to reduce the rate of heat movement, and in so doing that also reduces the ability for the system to dry.
And just to go back to those 3 things that you talked about before, conduction, convection, radiation, we're talking about convection here?
So we're talking about all 3. So heat transfer across a building is just by all 3 of those.
Okay.
In different ratios depending on what element it is. So conduction is a material property.
Yeah.
If I have a block of wood and I heat one side of that wood and I measure the temperature at the other end of that wood, then obviously I'm expecting very little heat transfer. Intuitively, we know that to be true, because wood is has a low thermal conductivity.
Yep.
By comparison, if I get a bit of steel, the other end will be hot to touch. And if I get aluminium, it'll be even hotter again.
Yep. So it's no steel houses, no aluminium windows with foil soffit.
All of those things. So really, intuitively, conduction is the thing that I think we all kind of get. We know that low thermally conducting materials are better.
Well, I get it now.
Yep. And so this comes to things like glass.
Yeah.
So everybody with their standard 4mm glass, oh, my windows are terrible. If only I had thicker glass. So, well, no, because glass as a material is highly thermally conducting. So if you can have a little bit of glass, it's poor thermal performance. If I have a lot of glass, it's still poor thermal performance. It's a material property. Yes, thicker glass has less heat transfer than thinner glass, but not significantly so in the way that changing the material has.
So it's with the glass, it's the low E coating, the R1 spacing that's really adding the value to spacer bars. Like that's where performance is coming through.
And so if you look at a window and say you have a single pane of glass and say, how can I improve the performance of this glass? Let's set aside the frame for a moment. Then the first thing you do is look at the conduction across that. Yep. So what do? I could go double glazing. And so what I'm trying to do then is to separate my 2 highly conductive elements, glass on either side, and trap in between a volume of a gas. your air, so in the usual or the easiest case. And by trapping air, the conductance of air is much, much lower than that of the glass. And so I reduce the conductance across that build-up. Yeah, and it's the huge benefit you'll see in going to double glazing. Now, the next one is convection. And so this, again, is an air mass that's holding heat energy, transferring from a warm space, say internally inside in winter, to the outside. And it carries that energy away, and that's not what we want to have happen. Now, if we use that glass of build-up as an example of this for a second, we accept that it's the air that's doing all the heavy lifting in that double glazed unit, then it would be intuitively reasonable to say, well, why don't we just build these with, say, 10 mil gaps or 16 mil air gaps? Why don't we build them with 30 or 50 mil air gaps instead? Shouldn't that perform better? And in terms of conductance, yes, absolutely it is better. But the problem there arises that you get convection. So you've got your interior surface of glass. So again, we're thinking a warm, heating-dominated climate. So it's warm, that interior face of glass. The exterior bit of glass is cold. And so the air that's trapped in that cavity, when the air gets near to the cold surface on the outside, it cools. What does cool air do? It drops and then cycles. It hits the glass on the inside, it goes warm, and you get exactly what Hamish and I've told about. It cycles around. It moves eddy currents. That is convection. So when I do that, I've now got this air that's moving. And so the air is carrying the heat energy from the interior face of glass towards the exterior. It touches the exterior face of glass. What does it do now? It transfers by conduction the heat energy into the outside pane of glass, which then conducts out towards the exterior. Is your brain tired?
No, it's not, because it actually makes a lot of sense. Because then it makes sense now that when you start, I guess, talking about double versus triple glazed, and Cam, please jump in if I say this wrong, because you can have a triple glazed unit with external glass, middle glass, internal glass, and that might be overall 32 mil thick, right? So I guess then it asks the question, well, why don't it still double glazed that's overall 32 mil thick? But the reason is that you've got the convection that happens within that DGU, and you don't get that same impact in a triple glaze because that convection is limited to a smaller space outside. And as you move through that wall, that bit of glass, it's lessens on the inside. Am I kind of spot on? Right.
Yeah, so exactly. So that's, if we just borrow, let's just say you can put a 24 mil air gap in between a double glaze. If you now whack a third pane of glass down the middle and split that into two 12 mil gaps, you've got the same total air layer conductance, 24 mil of air, but you've got two 12 mil gaps of air, and you don't get that convection falling as much. So if you've got a trapped air void, depending on the temperature difference inside and out, but certainly in an Australian climate, so where it gets to 0 outside and maybe 20 degrees inside in winter, then at about 12 mil or below, a trapped air mass won't have much convection to it.
So am I hearing right? And please don't answer this with, well, that depends. Am I hearing right that there is like an optimal gap between that? That depends.
It does depend, because it depends on the temperature difference.
And so it's really climatic.
And this is where we get so confused in the glass space between different test standards.
Yeah.
So in Australia, we probably shouldn't go down this rabbit hole here, but in Australia we go to AFRC, which is adopted from NFRC, the North American test standard, which uses very cold exterior air temperatures. I think it's minus 16 or something. I can't remember, I might have that wrong, but it's minus something. Far colder than we would experience in almost all Australian climates. And 20 degrees, say, inside. When you have that very high delta T, that temperature difference, say 35 odd degrees, then even at modest gaps, sort of 12 to 14 mil, you'll drive that convected air movement more rapidly. Whereas if it's only 5 degrees outside, plus 5, and 20 degrees inside, then the tendency for that air to start convecting, for those eddy currents to form, is far reduced. And so you could still go for, say, a 14 mil air gap and not have significant gan reference.
I want to go back a little bit for a second though, because we're sitting here talking about glazing in windows, but windows are a form of insulation.
Yeah. Obviously, I was just thinking before, there's potentially a whole podcast on talking about glass.
So while we're talking about insulation here, what we're talking about, I think, is probably, windows are a form of insulation. We've got this big structure, and all of a sudden we're cutting a hole in it, and it needs to perform as close to as we can on the walls. It's pretty much where, just wanted to keep everyone on track of.
And so let's jump across the insulation for a second. So our standard insulation is our bulk insulation, our bat, the woven glass wool usually thing that we get from our hardware store. How is that working? Well, it's glass, firstly, and we've already established that glass is highly conductive.
Yeah. Can I just stop just for 1 second? Because I do just want to take it back to glass for a second. And this is probably just sort of closing out that comment before when you said conduction, convection, and radiation is all relevant. And if we've talked about conduction, talked about convection in glass, could we also just quickly talk about how radiation is also a part of that glass unit?
This is one of my big gripes.
Yeah.
Is everybody talks about, oh, look, I've got double glazing. Fantastic. But that's like saying I've got a new car. What did you get, a Toyota? Getting a car doesn't mean anything, because the next question was asked is, what sort of car?
Yeah.
There's a hell of a big difference. In double glazing is exactly the same. There's double glazing and then there's double glazing.
Yeah.
There's a huge difference. And a lot of part of the difference is the size of that cavity we've talked about. Forget about the thickness of the glass. That's tertiary. It doesn't matter. Yes. How deep is the cavity? Has that cavity got a noble gas like argon in it? Because argon has less conductance than air, and you can tend to go for a deeper cavity with argon before you get those eddy currents forming.
And the air needs to be still, because this is going to lead to my second part.
And is that the reason why we have started to put gases in there? Well, okay, cool. So just to slow that convection.
And the better lower conductance of argon versus air.
Okay, so yeah, all right, now.
So adding argon to a double glaze unit gives you a improvement, throw around numbers, but maybe 10%. No, it's material, and it's relatively cheap and easy to do, and therefore we do it, but it's not massively changing the performance of that glazing yet. Where you get the real benefit is going for those things we call low E coatings. Let's again concentrate on our heating dominated climate. We've got long wave radiation coming from the sun. So hot things, the spectrum of heat energy generated tends to be a longer wavelength.
Yeah.
So the sun obviously being massively hot, long wavelength. It comes in, it strikes our glass, it gets towards the interior, it warms our interior spaces in winter, which is just what we want to have happen, and it heats our sofa and the floor and everything else. And then those materials warm up, but nowhere near as hot as the sun, and they emit shortwave radiation.
Is that like a bit of a thermal mass thing? Like, is that what you're saying in furniture? Because I've noticed in a house we just hand over, it's beautiful and comfortable, but it seems to not. There's like an emptiness of the heat, if that makes sense. Yeah. But until that, there was no furniture on this part yet, so the house is just open. We're about to hand over. When you go back there after it, it's the same. But it feels like there's more heat in it.
But depending on what the house is made from, by the time you add all of those, the furniture stuff, that's going to contribute massively to the thermal mass.
Yeah,
I think that's right. And tons of stuff we put in our buildings. Yeah. But we've got this shortwave radiation being emitted, and then it goes back and it goes through that glass towards the exterior. Now, the low E coating is a spluttered surface of fancy material. Silver is a closed component in it. And it's coated in your heating-dominated climate. It'll be coated on surface 3. Now, you count the glass surface from the exterior to the interior.
I was about to ask, where does it matter where it is?
Yeah, so you've got surface 1 is the outside bit that gets hit by the rain. Surface 2 is the inside of the outer pane. Surface 3, the one I'm talking about, is on the outside of the inner pane.
Yeah.
So it's facing towards our trapped air gap rather than full cap. And you put this splattered silver stuff on there, and that reduces the emissivity of that surface. So the radiation that can emit from that interior pane of glass is reduced towards the exterior.
Can you please explain what, and I don't even know how to say this, that emissivity, what does that mean?
It's a material characteristic that is the rate at which electromagnetic radiation can be emitted, can be sent away from the material.
Okay.
So different materials of different colour
Yeah.
have different rates of emissivity.
And that low E works by, in summer, it bounces the heat back in, and in winter, it kind of allows it to come through.
So this is where I think low E gets really, really tricky and people get confused, because I think we inherently think of low E first as a solar control glass, like something we will put on the house in Cairns or Darwin. Our sole objective is to stop that radiant heat from the outside getting in. And in that sort of climate, you would put the low E coat on surface 2, so on the inside of the outer pane, because you are trying to reduce the rate at which that heat that whacks the glass and then emit can radiate into the space. But it's a different chemical composition you use because you tune it to try and reduce the long wave radiation, because that's what's coming in from the sun.
So this is where, so I know there's houses where they accidentally put the glazing the wrong way around. So it's very important then where that outside, that sticker should always be on the outside, and you need to check your windows.
Yeah, it depends. It depends. It kind of does, because it also depends on the type of low E coat and a whole bunch of other stuff.
Yeah.
But rather than the coat, the surface onto which it's applied is the chemistry of that coating itself. So where I think we really go wrong, and this, to be fair, there is just debate about this, but when you look up your glass specification or you go your glass manufacturer, they will have a suite of options for low E coatings. And some of those are designed for your very your hot climates, your Darwiners and your Cairns, and they are designed to reduce that long wave radiation into the space and reduce the overheating. If you're in Melbourne, Hobart, Cradle Mountain, then that's probably not what you want. Other than 2 or 3 months of the year in the summer, you've got the other 8 months of the year when you want to get that heat into the space. And so then you use a different low E coating that has different characteristics to reduce the emissivity of the shortwave radiation. You typically put it on that surface 3 to try and improve the rate of heat retention of that glass within the space.
Are we talking about solar heat gain coefficient right now?
Correct.
Yeah. Okay.
SHGC.
Yes, so there's two phrases. There's SHGC that we would use in WERS and what we use in Australia, EFRC and FRE. And then in the European context, we use a thing called GIGA. They're similar but slightly different.
Is solar heat gain coefficient represented as a number?
Yes.
And
Lower the better, am I right?
I thought it was the opposite to you values.
Solar heat gain coefficient, or G,
Yep.
are a coefficient.
So solar heat gain coefficient is represented as a G, is that?
No, or G.
Or G.
G value for passive.
Oh, no, sorry. Yes, sorry.
G value was the phrase or the acronym we use in
Yep.
European context.
Yes, okay. Yeah.
Which is actually easy to understand too, I find.
Possibly, but both of them are coefficients. They have a value from 0 to 1.
Yeah.
If the coefficient, the SHGC, let's just use that one, is 1, that means all of the radiant heat that strikes that glass, it penetrates through on the other side.
Yeah.
And that's what you want if you're in Greenland.
Yes, okay, because you want to bring the heat in.
So which one? That's why you don't have no low E, you just want to have clear glass.
Yes, except
You want it the other way around. You want it to bounce back in.
Just to remind everyone right now, we're currently talking about radiation.
yes.
So currently talking about radiations. Right, no.
And yes, so we've established that an SHGC value of 1 means all the radiant heat comes through. A value of 0 intuitively means none of it comes through. And so Greenland, you want it as close to 1 as possible. In Cairns, you want it as close to 0 as possible. Now, in reality, you can't get either of those extreme values. And most of your, and this again depends on whether it's single, double, or triple layers, but your SHGC, heating dominant climate, say Canberra, Melbourne, Hobart, tends to have an SHGC something in the 0.5 to 0.65, 0.7 range. Whereas in cans, it'll be closer to 0.3.
And does your solar heat gain coefficient change? And I think I know the answer to this, from single to double to triple to whether you've got low E to whether you've got argent. Yeah, so that's where it's looking at the entire unit.
So glass is not glass.
No, yeah, that's right.
There's glass, there's glass.
And these low E coats are not usually visible to the naked eye, except maybe on a certain angle.
This is definitely not too far.
You've said a comment before that air is a great insulator for glazing, and I then want to now quickly move that to a conversation about ventilated cavities because we have an air gap. Does that mean the air in the ventilated cavities is also a great insulator?
No, could ventilate.
And so which means the convection is happening at a very fast rate?
You're, depending on how you do it, you're hopefully designing that ventilated cavity to be just that, ventilated. You want it ventilated because you want to carry away moisture and help drying of the assembly. And so doing that, inherently, you're going to be taking any heat energy in that cavity and chucking it towards the outside. Yes. So it offers almost zero heat retention of heat benefits.
So then when we have this metal sarping, as people would say, it's the insulation, it's a radiant barrier because it needs that air gap though. Is it actually insulating?
Yeah, okay, so it comes back to a couple of things here. So still air gaps. Yeah. So a shiny surface has a much lower emissivity than a matte dark color surface. And so the idea is it reflects that heat away, which is obviously desirable in a hot climate. If you want to get the optimum performance out of that foil or that shiny surface, though, you need two things. Firstly, you need to keep it shiny. And if you're putting it on a flat roof and we're not going to see it for the next 50 years, it's unlikely to remain shiny for very long.
I just was at a house doing the inspection last week and it's kind of exposed when we went up to the attic and it's always rotted away.
And then secondly, you need a still air gap adjacent. And usually we're putting these foils on the outside of our stove frame.
No air gap and no still cavity.
There's no air gap. Well, and if we do have a cavity in those foils, it's no longer a still air gap. And so the as-built performance of that assembly is significantly different to what you might test in a lab, where you have a still air gap next to a clean sheet of foil.
So you could say these metal sartings are a scam. In a housing environment. In a lab, it works. Oh. In a house, it wouldn't.
Yeah, I'm certainly not going to say they're a scam.
Can I also point out too that this probably also pokes a couple of holes in our star ratings as well, because a lot of the time the star rating includes your 1.5 R1.5 anti-con, which sits on top of your batten claddings, your roof claddings, and if you then got that ventilated cavity underneath that's moving, you can't then include that R value in your overall R value. But NatHERS does do that.
Yeah, and again, this is one of those, it depends, doesn't it? Because how ventilated is that?
Well, this is all pretty.
And from an insulation point of view, you don't want to ventilate that cavity at all. But from a moisture point of view, you absolutely do want to ventilate that cavity. So where does the balance lie? Yeah, and assuming, as I think we would all agree, we want durable buildings that don't rot out in 5 years, then we go towards we've got to deal with moisture first, bugger the energy. Yeah. And so you ventilate the space, in which case the thermal benefit of that foil-faced blanket sitting up on top of the roof truss is massively declined in a heat transfer towards the exterior context.
With that risk of going too much down a tangent, so in that ventilated cavity, what we're seeing is convection. Is that right? It depends. Or like
you're also seeing radiation, but predominantly that will be convection. Yeah.
Okay, so then if we're thinking about that, how we explain that scenario in a double glazed unit, does that impact that convection? And I'm thinking about like the size of the cavity here. Does that then impact how the insulation performs inside, like underneath that WIB? Or is it not impacted by the convection that's sitting on top?
What we didn't say at the outset is that insulation is all about still air gaps.
Yes.
That's all we're trying to do, is achieve a still air gap, because air is a really excellent insulator if we maintain small pockets of air that can't allow convection. So back to our...
So what's the maximum, maybe like 20, 22 mil?
Depends. It depends on temperature difference.
Yeah.
And so in an Australian climate where we don't tend to have -20 temperatures outside, the delta T, the difference between the inside and the outside temperature on a hot day or a cold day, is probably less than 20 degrees.
Yeah.
It's 40 degrees outside, 25 inside, or it's 0 out and 20 in. And so the ability for that air to convect is somewhat reduced than if the temperature difference was larger. But what we're fundamentally trying to do is create lots of tiny little pockets of air in our glass wool or in our foam, our XPS, EPS, PIR, whatever material it is. Lots of tiny little trapped voids of air.
We had a situation recently on a project where we're working on together. We had a cavity, and then the bats were only going to take up to, there was about 20 mil at the top of that where there was going to be a void because the bats didn't quite fill the void. And I just thought, oh, beautiful. There's trapped air in there. And I'll let you kind of finish off where we got to with this one, because I learned something that day.
So the issue with Guru, I think, is sort of a halfway house. If I have a trapped air void towards the cold side of a construction.
Yep.
So imagine, say, a roof truss construction where I run my insulation at the ceiling fine, and then I have a void above before I get to my sarking and then my outside. I have this trapped mass of cold air in the winter period, and that's a big depth, so far more than 12 or 14 mil. So there's a chance that you're going to get convection, and that air will move, and any moisture that gets up into that space can then be picked up by those eddy currents and carried around in ways that are not entirely predictable.
So when we build Italo, cavity batten, plaster, is that air gap still? If we didn't put insulation there, how still is it?
So that's...
Because it's on the inside, it's not we are running.
So let's assume you're putting a 35 mil batten.
Yeah.
Pretty typical,
Yeah.
probably. That will have some air movement, but not much, because there's not a big delta T. It's only once you get into where the insulation is between your Italo or your external grab that you have a temperature difference and a risk of convection form.
So when you are doing the PHBP, do you allow that, if there's no insulation in zone, do you put a value in there still?
So if you're going to be conservative, you've given no value.
Yeah.
We would normally give it a value because it is, as you say, essentially a still air.
Yeah.
So what Matt was saying before, there's less risk on the warm side, and in our scenario, there was a higher risk because there was quite a potential of a drastic temperature differential from the inside to the outside,
because we had a significant amount of the insulation. There was like R4 or something. Yes, on the warm side. So if you think again, 0 degrees outside, 20 degrees inside, if I've got R4 of insulation, by the time I get to the outside face that I'm getting pretty cold, if I then put, say, a photo face blanket above that, which is R1.5-ish, then I've already reduced, a good 2/3 of my temperature. So I've gone from 20 degrees on the top side of that R4 insulation. I'm now maybe around 12 or less degrees. And that almost certainly is below dew point.
Yeah.
And so we've got this trapped mass of cold air that possibly is going to convect. And there is a chance that I'm going to have moisture issues.
So even though that we probably did in some areas compress the insulation a little bit, the risk was, the benefit of that is that we weren't allowing any air to move, in summary.
That's right. So your glass wool is of a sufficient density that you're trying to restrict the ability for convection, air movement through that material.
Yeah.
Now, that doesn't mean if you've got pressure difference in and out, obviously glass wool is not an air tightness. You can get a hair blow on one side and you'll feel air blowing through the other side. That's not what we're talking about here. It's the temperature-driven air movement. So delta T across that glass, is it going to drive those eddy currents in that?
And that's convection.